Let me check once. Okay, so it was all right from my side. The signal was clear. Everything is live. Any issues, please let me know in the chat box so that we will adjust the issues. Okay, guys. So welcome to session 2, part 2 on a quick review on Synchronous Machines course. So welcome to GATE Champions series that we are conducting from past few days. So the session 1 already completed. If in case if you didn't watch session 1 or part 1 of this Synchronous Machines course, I mentioned that link in the description. So you can go through description, you will find the link and you can watch that particular lecture. Okay, so then session 2 will become more easy. All right. So in the previous lecture, when we had a discussion about synchronous machines, we covered all the basics. Also, we have seen EMF equation of an alternator. We discussed about armature reaction, equivalent circuit, phasor diagrams of both generator as well as motor. Okay. So now let us start session 2 with another important topic, that is voltage regulation of an alternator. Okay. So first we will see what is the basic definition for voltage regulation, a very important parameter to understand the working principle of performance of any machine. So we will calculate voltage regulation in transformers, we will calculate voltage regulation in DC generators and also in synchronous generators. Okay, so I hope the session was clear. So let me check once again to avoid any problems. Yes, very good evening guys, very good evening, thank you. Yeah, so please share this session to your friends. Okay, so let them also join so that it will be more interesting. Any questions related to the discussion, please post your questions in the chat box. Okay, so at the end of the session, I will try to give you the answers. All right, okay, fine. So let us go through the definition first of all. Yes, voltage regulation is defined as the change in terminal voltage from no load to full load. Okay, the change in terminal voltage from no load to full load, and it is defined as EF minus VT by VT into 100. Please remember here EF is nothing but no load terminal voltage. Okay, this is no load terminal voltage. Okay, and VT is nothing but full load terminal voltage. This full load terminal voltage is indirectly busbar voltage generally. Okay, suppose if there is any numerical question from voltage regulation, especially in per unit values, you have to consider this terminal voltage as 1 per unit. Okay, suppose if the machine was connected to infinite bus bar, generally the terminal voltage will be equal to 1 per unit. Okay, so EF minus VT by VT into 100. So where EF is the no load terminal voltage, VT was full load terminal voltage. Okay, so now generally in order to conclude a machine is better performing or poor performing, yes, you can answer that question just calculating voltage regulation, right? Yes, you can conclude a machine is performing better if voltage regulation is very low. If voltage regulation is high, you can conclude it is a poor performance. Okay, because voltage regulation represents the change in voltage from no load to full load. Okay, and generally plus or minus 5% regulation is acceptable. Okay, fine. Now the question is how to find out voltage regulation. You just need the magnitude of EF and VT. Remember, you have to consider only magnitudes. Only magnitudes. Generally, if you go through the equivalent circuit, EF will be leading VT by an angle delta. But while calculating regulation, don't take that angle into picture. Okay, suppose let us say I gave you a question like this. EF is equal to 100 volt at an angle 30 degrees. VT is equal to 90 volt at an angle 0 degrees. Then what is the formula for voltage regulation? It is simply 100 minus 90 by 90. That's all, only magnitudes. Don't take 100 at an angle 30 minus 90 at an angle 0 by 90 at an angle 0. That is wrong. Okay. So voltage regulation means it is the change in terminal voltage magnitude from no load to full load. Okay. Now we have to discuss two important cases. One is what is the condition for zero voltage regulation and what is the condition for maximum voltage regulation. We used to study the same concepts even in transformer as well. Okay. So see, zero voltage regulation is possible only for a leading power factor load. Okay. Yes, not all leading power factor loads. At one particular leading power factor value, voltage regulation will be definitely 0. Okay, leading power factor load. And the condition is, yes, you have to remember this condition, guys. Cos theta plus phi is equal to minus Ia into Zs by 2 Vt, and remember every value is per phase values. We have to use only per phase values. Why? Because this particular condition we will derive from the equivalent circuit. And equivalent circuit is always drawn per phase. Therefore, definitely these all values are per phase values. And here, what is this theta is representing? Yes, theta represents synchronous impedance angle. Synchronous impedance angle. Understand? And you can write, in the equivalent circuit we have two parameters, armature resistance and synchronous reactance. So the synchronous impedance angle theta can be written as tan inverse imaginary part xs by real part Ra. Understand? That is synchronous impedance angle. And this phi represents load power factor angle. Load power factor angle. In fact, this is the angle at which voltage regulation will be equal to 0. And Ia is armature current, Zs is synchronous impedance, Vt is terminal voltage. Only magnitudes you need to consider. Magnitude of Ia, that is a full load current. Okay, and magnitude of Zs, what is Zs magnitude? Square root of Ra square plus Xs square, and Vt magnitude. Okay, so if you solve this equation, you will get a power factor angle phi, and that is the angle, that is a power factor angle at which zero voltage regulation can be identified. Okay, and if you further proceed to the derivation, we can understand that generally voltage regulation can be obtained. Zero voltage regulation is possible for a leading power factor load, near to unity, guys. Near to unity. That means generally the power factor will be around 0.9 to 0.95 leading. So this is the load power factor range where you can find out voltage regulation is equal to 0. Understand? Okay. We are not doing the derivation. I hope you should be able to remember this. Okay. This is about zero voltage regulation. Now let's talk about maximum voltage regulation. As the word itself is representing, it is the maximum possible regulation from that particular, alternator. Yes, read that. Maximum voltage regulation is possible only for lagging power factor load. Okay, zero voltage regulation is possible only for leading power factor load. Maximum voltage regulation is possible only for a lagging power factor load. Okay, and the condition is phi is equal to theta. Again, phi is the power factor angle, theta is the impedance angle. Where theta is impedance angle, we know impedance angle tan inverse xs by Ra. Okay, generally, inside alternator, Ra is very small or very large. Yes, we will always design armature winding to have very low resistance. Therefore, Ra is generally very small. As Ra is very small, armature circuit is highly inductive because this reactance is dominating. Therefore, this theta, impedance angle theta, will be around 80 degrees to 85 degrees generally. Why? Impedance angle is almost near to 90 because we are designing armature to have very low resistance. So therefore, synchronous reactance is the dominant component. So impedance angle is near to 90 degrees. If impedance angle is near to 90, can I say power factor angle is also near to 90? Okay. Therefore, at what power factor ranges we can get zero voltage regulation? I can write, yes, zero voltage regulation is possible for lagging power factor loads near to zero. Understand? Generally, the power factor range will be 0.1 to 0.2 lagging. So this is the range of load power factor generally where you will find zero voltage regulation. Understand? So maximum regulation is possible almost near to unity power factor on the leading side. zero voltage regulation is possible almost near to zero lagging, okay, on the lagging side, okay, right. So this is about a condition for zero voltage regulation and a condition for maximum voltage regulation. Now using these conditions, we can draw regulation curve. Okay, so similar type of regulation curve we will even draw for, a transformer also. So what we will do is that we will take positive voltage regulation on the y-axis here and a negative voltage regulation here. Okay, so now I will be taking power factor on x-axis. Let us select lagging power factor on the right side, leading power factor on the left side, load power factor. So here you have unity power factor. Now let us understand the condition for zero voltage regulation first. So the y-axis value voltage regulation will be 0, yet leading power factor means left side near to unity. So somewhere here voltage regulation will be 0 and this is unity. Somewhere let us say this is 0 lagging. So here we have a 0 leading, ZPF leading power factor. This is unity. Next, maximum voltage regulation. Imagine this is the maximum voltage regulation, and the maximum voltage regulation is possible for leading power factor or lagging power factor. Lagging power factor, that is the right side of the curve, okay, right side of the graph, near to 0. Somewhere here, maybe 0.1 or 0.2 lagging, we will get maximum voltage regulation. Okay, somewhere here, maximum voltage regulation will come. And at unity power factor, you just join these points and you extend this curve. Yes. So this is generally what we call it as a voltage regulation curve of an alternator. And remember, the same curve is valid even for a transformer also. Only the values may change slightly, but the curve almost going to be same even for a transformer and also for transmission line. Even in power system subject, in a transmission lines also you will calculate voltage regulation, right? And a similar type of curve will come. Okay, so what is your observation? At unity power factor, voltage regulation is definitely positive, a small finite positive value. Understand? Okay, so this is voltage regulation curve, and you can give some conclusions from this curve. You see that you see this is the point where voltage regulation was 0, guys. Okay, now left side of this you can see this curve is negative. Am I right? Negative voltage regulation. Okay, so this is negative voltage regulation region. From this side onwards, from this point onwards, this is positive voltage regulation. This is positive voltage regulation. So left side of this point, this is all negative voltage regulation. From here onwards, this is positive voltage regulation. Now one more important observation is, you take any lagging power factor, that is right side of the x-axis, you take any lagging power factor, voltage regulation is positive. Okay, so for all lagging power factors, including unity power factor, voltage regulation is positive. But if you come to the leading side, some of the leading power factors offering negative voltage regulation, and at one leading power factor, 0 voltage regulation is also possible. And certain leading power factors, this is positive regulation, right? This is a positive voltage regulation because we are, remember, we are still on leading side. Okay, so leading power factor, positive regulation. Next, this point, leading power factor, 0 regulation. What about this curve? Leading power factor, negative regulation. Therefore, when the power factor is leading, 3 choices are there. It may be positive regulation, it may be 0 regulation, or it may be negative regulation. But if you come to the lagging side, you take any lagging power factor, voltage regulation is always positive. Understand? So this is what we call it as voltage regulation curve of an alternator. Got it? Okay, now what we will do is that we will try to answer a simple question related to voltage regulation. Understand? Now let's answer a question related to voltage regulation of an alternator. Okay, so let's see. Look at this problem. A single phase 2000 volt alternator has armature resistance and reactance of 0.8 ohm and 4.94 ohm respectively. The voltage regulation of the alternator at 100 ampere load at 0.8 leading power factor is how much? See, the question is about a single phase. Okay, So as it is a single phase, no need to worry about line values and phase values. 2000 volt alternator, therefore obviously that 2000 is the terminal voltage of the alternator. Okay, that is the bus bar voltage indirectly. Armature resistance was 0.8 ohm. 0.8 ohm. Synchronous reactance was 4.94 ohm. Okay, and we are asked to calculate voltage regulation of the alternator at 100 ampere exactly. This is the armature current indirectly. 0.8 leading power factor. So armature current was 100 ampere. Power factor means cos phi. So cos phi is 0.8 leading. Okay, so what is the voltage regulation is the question. All values are in percentage. Percentage regulation we have to calculate. So what I will do is that based on the given information, find out the no load terminal voltage indirectly EF. Okay, so what is the formula for EF? If I go to the next page, EF is equal to square root of Vt cos phi, okay, plus Ia Ra whole square plus Vt sin phi plus or minus Ia XS. But what is the power factor given? Leading, and it is a generator. Generator leading power factor means it is minus sign. Minus Ia XS whole square. This is the induced EMF. If it is a three-phase machine, you have to use phase values, but the given machine is a single phase, so direct values you can use. Okay, so if I substitute square root of, what is the Vt value given? 2000 volt. Power factor is 0.8, right? Cos phi is 0.8 plus armature current was 100, and what is armature resistance? 0.8 whole square plus Vt sin phi. Vt was 2000. Can I say cos phi 0.8 means sin phi becomes 0.6. Therefore, this is 0.6 minus Ia was 100. XS was 4.94 ohm. Okay, directly I substituted. Now you will get directly what is the value of EF. So let me calculate this. Okay, just to substitute everything. 2000 into 0.8 plus 100 into 0.8, that is 80 whole square plus 2000 into 0.6, 1200 plus minus 100 into 4.94, that is 494 whole square. So I am getting 1822 volt. 1822.31 volt. Okay, if I made any mistake in my calculator, please correct them. Okay, right. So now I have EF value with me and Vt value with me. Then what is the formula for percentage voltage regulation? So percentage voltage regulation is equal to EF minus Vt by Vt into 100. Got it? So what is EF value? We just calculated 1822.31 minus terminal voltage Vt, that was 2000, divided by terminal voltage 2000 into 100. So if you complete the calculation, we will get directly what is the voltage regulation. Yes, I am getting minus 8.88 percentage. Minus 8.88 percentage, a negative regulation. So let us go back. Yes, I think option B was satisfied. Minus 8.88 percentage, approximately minus 8.9 percentage. A very simple question. This was given in GATE 2000 paper. So suppose if the same question was given in percentage values, this will become line voltage, guys. Convert to phase voltage. Vt is equal to 2000 by root 3. And this will become line current. And if it is a star connected machine, line current or phase current both are same. Okay, you can directly use 100 ampere. Then you will get EF also per phase. Then you take EF minus Vt by Vt into 100. Okay, so you need to be very careful, especially when the machine is a three-phase machine. Okay, so this is an example question related to voltage regulation of an alternator. Okay, fine. Now we will move to our next topic, that is characteristics of alternator. Okay, so there are many characteristics for alternator performance. To understand the performance of alternator, all characteristics are not important for us. These 4 characteristics we have to discuss. So open circuit characteristics, short circuit characteristics, zero power factor characteristics, and external characteristics. So we will see one by one quickly. So let us understand what is open circuit characteristics. Remember, open circuit characteristics is also known as no load characteristics or magnetization characteristics of alternator. Okay, so no load. You can also write it as no load characteristics. As we are drawing the graph under no load condition, you can see here, this is the rotor part of the machine. Rotor means a field circuit. This is the stator part of the machine, which is nothing but armature circuit. And you see the terminals of the armature are connected to any load or open circuited right now, open circuited or under no load condition. Therefore, what is the magnitude of armature current? Yes, armature current will be equal to 0. So first let us try to understand between which parameters we are going to draw the open circuit characteristics. Okay, remember, open circuit characteristics are drawn between open circuited terminal voltage, that is nothing but indirectly EF, with respect to field current. That means our aim is, by changing the field current value, how the induced EMF of the alternator was changing, we wanted to observe it. Okay, if a field current changes, how the induced EMF value was changing, we wanted to observe it. That is why we are drawing this graph. So first of all, how to do this particular experiment in the laboratory? Suppose, I hope you might have conducted this experiment in your college laboratories. So I need two values, guys. One is y-axis value, which is equal to induced EMF. Another one is the x-axis value, which is equal to field current. So when you are doing this experiment in the laboratory, how do you measure field current? Very simple. You connect an ammeter here. You connect an ammeter in field circuit, automatically it will measure field current. Next, what is the y-axis value? Induced EMF. To measure induced EMF, you connect a voltmeter here. That will measure actually terminal voltage, right? Because the voltmeter was connected at the terminals. But I need EF on y-axis, not VT. Then how do I do that? Very simple. Right now the machine is under no load condition. That's why the current was 0. When current was 0, there is no drop internal to the machine, right? Actually, if you look at the equivalent circuit, this is induced EMF EF. There is resistance and synchronous reactance, correct or not? And finally, we have terminals here. So when armature current was 0, can I say there won't be any drop in this impedance? If there was no drop in this series impedance, terminal voltage and induced EMF both are equal. So therefore, measuring terminal voltage is indirectly equal to measuring induced EMF. Got it? But important thing is, we are connecting the voltmeter between two lines. Therefore, voltmeter will measure line voltage. It will measure line voltage. Okay. But in the calculations, we must always use phase values only. Okay. So let's see what are the observations. First, we will try to make sure that IF is equal to 0. That means the field current is equal to 0. What happens, guys? If a field current is 0, ideally there is no field flux in the machine. But practically, even though field current is 0, a small flux will be always available in the machine known as residual flux. Okay, we know that any ferromagnetic material, even though excitation was not given, a small amount of flux is always retained by the material known as residual flux. So because of that residual flux, even though field current is equal to 0, a small EMF will be induced. We call it as residual induced EMF. Okay, so we call that EMF as residual EMF. See, x-axis field current is 0, but y-axis EMF is a very small value. We call it as residual induced EMF. Okay, next, what happens if I increase the field current? If a field current increases, obviously field flux will increase. If a field current increases, field flux value will be increased. Whenever field flux increases, can I say generated EMF value will also increase? Why? Because we have EMF formula directly. What is the formula for EMF? 4.44 into field flux into frequency into number of turns into winding factor. So whenever this field flux is increasing, automatically this EMF also increases. Therefore, as x-axis field current is increasing, this y-axis EMF will be gradually increased like this. That means the EMF shape will depend upon the flux shape. Flux will never be like a straight line, guys, because non-linearity will be there in the magnetization, right? Any practical core material will have magnetic saturation effect. So the curve is always non-linear. You won't get like a straight line. Got it? Okay. Now, question is how far this flux is going to increase? Flux will increase forever or up to certain extent? Yes, up to certain extent flux will increase. Beyond that, flux will reach saturation. Imagine at this point, let us say flux reaches to saturation. Okay, imagine this is the saturation point. Okay, so once the saturation reaches, flux will not increase linearly, it will increase non-linearly. Okay, generally what happens beyond saturation? Beyond saturation, even though field current increases, EMF does not increase linearly, it will increase by a very small quantity, just like this. You can see here. It won't be exactly constant, guys. It will slightly increase because of saturation effect. Okay, so this point is what we call it as knee point. So what is your observation? Before the knee point, whenever field current increases, flux will also increase. But after knee point, flux is almost saturated. Therefore, you will find a very small amount of increment in the voltage. Understand? Generally, we don't recommend the machine to be operated in the saturation zone. Why? Because in the saturation zone, a small increment in EMF demands a large increment in field current. Because of large field current, there is a chance that field circuit may overheat. Therefore, generally, we don't recommend the machine to operate in the saturation zone. So, this is open circuit characteristics. Up to knee point, it is almost like a linear curve. Beyond knee point, it will be a non-linear curve. And remember, there is a small voltage induced when field current is zero. We call it as residual voltage. As I mentioned, it is very small. You can almost neglect it. In case if you neglect residual voltage, this curve would have started from origin. Understand? Okay. This is open circuit characteristics of an alternator. All right. Now let us try to understand short circuit characteristics. As the name itself is indicating, we are drawing the curve when the terminals of the alternator are short circuited. Okay, let me draw a simple circuit. Imagine this is the field circuit of the alternator. We are exciting this field winding with DC supply. This is a field voltage and the current is a field current. That field current will create a flux. We call it as a field flux. That field flux will cross air gap and link armature winding. An EMF will be induced. We call it as a field induced EMF. And then we have armature resistance, synchronous reactance, and finally the terminals are available here. These are the terminals. But now the terminals are short circuited. Short circuited terminals. Got it? Because we are drawing short circuit characteristics. Okay, short circuited terminals. These two together I can call it as a synchronous impedance ZS. Okay, now point is very simple. As the terminals are short circuited, terminal voltage will be zero. Got it? Now remember, as the load is short circuited here, a very small amount of EMF will be generally sufficient to circulate rated armature current. I repeat, when the load was short circuited, it is almost like a fault condition indirectly. As the load is short circuited, a small voltage will be sufficient to circulate rated armature current. But what if the voltage is rated value? Suppose if this voltage is rated value and the load is short circuited, then a small current will circulate or very large current will circulate, then very large current will circulate. Okay, but if very large current is circulated, armature winding will overheat, so machine may damage. Okay, so we wanted to circulate rated current only. For that purpose, a very small current will be sufficient. Sorry, a very small EMF is sufficient. Question is, who will control this EMF, guys? Can I say this EMF is mainly depend upon field flux? Who will control field flux? Field current. Therefore, let us understand between which parameters short circuit characteristics are drawn. Short circuit characteristics are drawn between short circuited armature current with respect to field current. With respect to field current. And if you write a KVL equation here, if you write a KVL equation, can I write EF is equal to IA into ZS simply? IA into ZS. From this, you separate IA value. Therefore, IA during a short circuit condition is simply equal to EF by ZS. Important equation. This is the formula for short circuited armature current. Therefore, the magnitude of the current will clearly depend upon induced EMF. What is the formula for induced EMF? Induced EMF is equal to 4.44 into field flux frequency number of turns into winding factor. Therefore, can I say from the formula EF is directly proportional to field flux? Next, field flux will depend upon which current? Field current. I can write field flux is directly proportional to field current. Therefore, overall what is observation? Short circuited armature current will depend upon EF. EF will depend upon phi F. Phi F will depend upon IF. Therefore, finally, what is the relation between short circuited armature current and field current? Can I say direct proportionality? Therefore, if you draw this short circuited characteristics, it will be like a straight line passing through origin. It will be like a straight line passing through origin. Why it is like a straight line passing through origin? Because direct proportionality. Short circuited armature current and field current both are directly proportional. So it will be like a straight line passing through origin. But our aim is, I wanted to understand at what field current rated armature current will circulate. Imagine on the y-axis, just a moment. Yes, on the y-axis, this is rated armature current, let us say. Rated armature current. So this rated armature current can be generated at how much field current? A small field current. Why a small field current is sufficient? Because I told you, as the terminals are shorted, to circulate rated armature current, we need a small EMF. To induce a small EMF, we need a small field current. That's all. Okay. So therefore, rated armature current can be observed when field current is very, very small. Got it? And you don't do the experiment till the end of this curve, guys. You can just extend the line. Okay, extend the line. Could you tell me, or could you try to understand why there is no saturation effect in short circuited characteristics? Why there is no saturation effect? Because the reason is very simple. During the short circuit condition, what are the only parameters available in the circuit? RA and XS. There was no load. Load is shorted. But we know one thing, RA is very small. Generally, we will design armature circuit to have very low resistance compared to synchronous reactance. As RA is very small, just neglect it. What happens if I neglect armature resistance? Can I say the only parameter available is XS only? And XS is an inductive reactance. Therefore, this armature current is simply passing through a pure inductor. Therefore, is it looking like a voltage source in series with pure inductor? Therefore, what is the power factor of the circuit? ZPF lagging. Okay, so during a short circuit condition, alternator will operate at 0 power factor lagging condition. And we know when power factor is 0, that too lagging, what is the nature of armature reaction? Pure demagnetization. We studied armature reaction already. Pure demagnetization. Pure demagnetization means what? Whatever armature flux is created, that will directly oppose main field flux. That means, can I say resultant flux has a chance to decrease, but there is absolutely no chance to increase. Why? Because armature flux is directly opposing it, demagnetization. So as resultant flux may decrease, may not increase, that's why saturation is avoided. Generally, when saturation will come when resultant flux is increasing up to a certain value, it will increase, later it will reach saturation. But here, absolutely no chance for magnetic saturation since it is a pure demagnetization. Got it? So, saturation can be neglected during a short circuit characteristics. That's why the curve is linear. Okay, that's all. This is about short circuit characteristics. Now, we discussed open circuit characteristics and short circuit characteristics. Using these two, we can identify or we can calculate synchronous reactance of the alternator. Okay, yes. So, measurement of ZS. I wanted to calculate synchronous impedance. Okay, see this. You can use this KVL equation. Can I say this is the equation under which condition? Short circuited condition. So, I will rewrite it again. At a short circuit, what is the formula for armature current? This is equal to EF by ZS. My aim was to calculate ZS value. So therefore I can separate ZS. Is it looking like EF divided by armature current during a short circuit condition? Yes. So if you wanted to calculate, remember every quantity must be per phase only. Even though meters are giving you line values, convert them to phase values. Okay. So to calculate ZS, I need two values. One is EF, another one is armature current at short circuit. Got it? So armature current during a short circuit, I can easily measure by connecting an ammeter here. If I connect an ammeter, that ammeter will measure armature current during a short circuit condition. Then how do you measure EF value? Remember, EF is a voltage internal to the machine. You can't connect a voltmeter going inside the machine, right? It's not possible. What the thing is, you can connect voltmeter only on the terminals of the machine. You can only connect a voltmeter at the terminals. You can't connect inside the machine. But the terminals are shorted, right? If you connect a voltmeter across a short circuit, it will measure zero voltage. Then how do you measure EF? Very simple. So to measure EF, what you need to do is that open circuit this. Open circuit the terminals. When I open circuit the terminals, what happens to current? Zero. When current is zero, there is no drop in this impedance. If there is no drop in the impedance, now you can connect a voltmeter here. This will directly measure EF. Why it will measure EF? Because there is no drop in the impedance. So directly EF will appear at the terminals. That means this EF must be calculated when the circuit is shorted or open circuited. Open circuited. That means, can I say this EF is open circuit terminal voltage, and armature current was short circuited armature current. Therefore, ZS is indirectly equal to open circuit terminal voltage with respect to short circuit armature current. Short circuit armature current. Okay, so open circuit voltage is given by OCC characteristics. Short circuit current will be given by short circuit characteristics. But remember, this open circuit voltage and short circuit current both must be measured at same field current. Okay, that means see, right now the terminals are open, therefore I will get EF. Let us say I measured EF at a field current of 5 ampere, guys. When a field current is at 5 ampere, I got open circuit terminal voltage is equal to, let us say, 200 volt. How do you get a short circuited armature current? Simple. Short circuit the terminals now. Okay, now short circuit the terminals. That means short circuit test indirectly. The moment I short circuit the terminals, short circuit current will flow. Measure it using ammeter. But while I am coming from open circuit to short circuit, am I changing this field current? No. That means open circuit voltage was measured when field current was 5 ampere. And now I am measuring a short circuit current also. Let us say short circuit current comes as 150 ampere. That is also measured at the same 5 ampere field current. So both must be measured at the same field current. Then only you will get correct value of synchronous impedance. So what is the formula for synchronous impedance? It is the ratio from open circuit terminal voltage to short circuit armature current, and the unit will be ohm per phase. Got it? And if you draw a curve, okay, I'm not doing the derivation directly, I'm drawing the curve. If you draw a curve for synchronous impedance with respect to field current, so initially synchronous impedance is a constant value up to saturation point. Later the synchronous impedance will decrease in a non-linear fashion like this. Got it? So this is what we call it as saturation point. Okay, so before the saturation point, synchronous impedance is a constant value. So this is unsaturated synchronous impedance. After this point, synchronous impedance is reducing in a non-linear fashion. This is saturated synchronous impedance. Got it? So generally we will operate the machine in a slightly saturated mode where we will calculate adjusted synchronous impedance. That's a different thing. Okay, I'm not doing the derivation, but this is how synchronous impedance actually looks like. Understand? So now we completed open circuit characteristics, which will give induced EMF information, short circuit characteristics, which will give short circuited armature current, Using both of them, we calculated synchronous impedance of the alternator. Got it? Okay, so let's move to the next one, that is zero power factor characteristics. Okay, right. Coming to zero power factor characteristics, the next one. Okay, so we have seen open circuit characteristics and short circuit characteristics right now. Now let us try to understand zero power factor characteristics. Okay, so very simple characteristics. First of all, why the word zero power factor is used? Very simple. While drawing these characteristics, we will connect a pure inductive load on the terminals of the alternator. Okay, so that means you see, suppose, just a moment. Okay, so let us say this is the field circuit of the given, synchronous generator. This is the field voltage Vf and field current. And coming to armature, we have an EMF induced, and this is armature resistance, and here we have synchronous reactance. Okay, now on the terminals of the alternator, we will connect a pure inductive load. Okay, so let us say there was an inductor with many number of turns like this, and we will connect this inductor to the alternator. Inductor means what is a power factor? ZPF lagging. Therefore, the characteristics are named as zero power factor characteristics. So let us say this inductor has some number of tappings on it. Okay, so let's say this is tapping number 0, 1, 2, 3, 4 like that. So initially we will connect the alternator to tapping number 0. When I connect alternator to tapping number 0, can I say the terminals are indirectly short circuited? Yes. And then we will step up the tapping one by one. Let's connect alternator to tapping number 1 next to 2, next to 3 like that. So whenever I step up the tapping position, indirectly the load inductance is increasing. That is the meaning of it. And we will try to maintain armature current at rated value. At any tapping position, you try to maintain armature current rated value. So first let us understand between which parameters these zero power factor characteristics are drawn. So remember, zero power factor characteristics are drawn by taking terminal voltage on y-axis and we will take field current on x-axis. But while drawing these characteristics, we have to maintain armature current at a constant, that too rated value. Our aim is to make armature current constant and also rated value. Okay, so let us draw the characteristics. So first of all, when I keep the terminals at a tapping number 0, indirectly can I say the terminals are short circuited? If the terminals are short circuited, the y-axis value will be equal to 0. During this condition, as the terminals are short circuited, we know a small EMF will be sufficient to circulate rated current. And to induce that small EMF, you need a small amount of field current. Therefore, when y-axis value is equal to 0, we need a small field current. Let us call it as IF naught. What is IF naught? It is the amount of field current required to circulate rated armature current when the terminals are short circuited. Okay, IF naught. Got it? Now, what will happen if I step up the tapping? If I step up the tapping, indirectly can I say load reactance increases? When load reactance increases, automatically the current will decrease. But I wanted to maintain this current at a constant value. So therefore, whenever load reactance increases, you increase this EMF to maintain this current constant. How to increase this EMF? By increasing field current. Therefore, whenever tapping position increases, we have to increase the field current. Let us say I am increasing the field current from IF naught to IF1. And now the tapping is at position 1 indirectly. So see, the terminals are connected to position number 1 now, like this. When I connect to position number 1 now, load reactance is not 0. Therefore, terminal voltage is not 0, a finite terminal voltage. Okay, so therefore, y-axis terminal voltage is a finite value. Let us say VT1. Okay, so right. Now similarly, if I further step up the tapping, the field current requirement will further increase. Terminal voltage value will also further increase. You'll get one more operating point like this. And if you join all these points, you will get zero power factor characteristics. Okay, this is what we call it as zero power factor characteristics. Okay, so particularly I can say zero power factor lagging characteristics. Got it? Okay. And this will be useful in calculating voltage regulation by using a Portier triangle method. Understand? Okay. Now, the final one, external characteristics of an alternator. So, external characteristics are drawn between external voltage to external current. External voltage means terminal voltage. External current means load current. Okay. So, see here, assume this is the field circuit of alternator. We are exciting this field winding using a DC supply that will induce an EMF in armature winding. We call it as a field induced EMF. And then there is a synchronous reactance. Actually, resistance will also be there. I am neglecting it because it is very small. And then the terminals are connected to load. Actually, load will be connected here. Okay, so the voltage across the load, we call it as VT. Current passing through the load is nothing but armature current IA. Now, we need to draw a graph between this VT and IA. Okay, the graph is drawn between VT and IA. That means whenever load current changes, how the load voltage was changing. That is the study. And while drawing these characteristics, we have to maintain field current at a constant rated value. Okay, field current is constant. When field current is constant, field flux is also constant. That means EMF is a constant value. This EMF is a constant value. But our graph is drawn between EF and IA or VT and IA, VT and IA. So can I say if EF is constant, VT value will completely depend upon drop across this reactance. Okay, that means indirectly voltage regulation. Okay, suppose if the machine is under no load condition, suppose armature current is 0. If current is 0, no drop in this impedance. Therefore, entire EF will appear across the terminals. So therefore, at a no load current, terminal voltage is simply equal to induced EMF. Okay, induced EMF. Next, what happens if load current increases? If load current increases, drop across this reactance will increase, then terminal voltage will decrease if it is lagging power factor. Okay, if it will increase if it is leading power factor. Why? Because we studied voltage regulation concepts, right? Voltage regulation will be positive for lagging power factors, and for some leading power factors, voltage regulation will be negative. Negative regulation means rise in voltage. Positive regulation means drop in voltage. If you consider unity power factor, slight drop will be there. Unity power factor will also offer drop only. Why? Because positive voltage regulation. Okay. When do I get zero voltage regulation? That is a flat curve. Yes, we know condition for zero voltage regulation is leading power factor near to unity generally. Okay. And if you draw few more curves, see, this is ZPF leading, guys. Zero power factor leading. This is like 0.8 leading. This is like 0.6 leading. Okay. Like this. This is near to ZPF lagging. Maybe I can say, yes, this is 0.8 lagging. Not 0.8, I must say near to 0, right? Near to 0 means let's say 0.4 lagging. 0.4 lagging. This is near to unity, 0.8 lagging, something like that. So for most of the power factors, especially lagging and unity power factors, machine will offer drooping voltage characteristics. And for most of the leading power factors, rising voltage characteristics. Got it? Okay. This is about external characteristics of synchronous generator. Okay. So we have seen open circuit characteristics, short circuit characteristics, and using open circuit and short circuit characteristics, we understood how to calculate, synchronous impedance, and then ZPF characteristics and external characteristics. These are sufficient, to solve questions related to characteristics of synchronous generator. Okay. Now let us try to answer few questions. Okay. Right. Let's see some questions. Now look at this question. This is a question from GATE 2014 paper. You can read the problem. It was a 2 marks question. A star connected 400 volt 50 Hz 4-pole synchronous machine gave the following open circuit and short circuit test results. Open circuit voltage was 400 volt at field current of 2.3 ampere. Short circuit current was 10 ampere at field current of 1.5 ampere. What is the value of per phase synchronous impedance at rated voltages? We are asked to calculate what is per phase synchronous impedance. Okay, so you all know that we studied already the formula. Synchronous impedance is equal to open circuit terminal voltage divided by short circuit armature current. But important thing, both of these must be measured at same field current. That is the problem here. You see that open circuit test, the voltage was 400 volt. It was measured at a field current of 2.3 ampere. Short circuit current is 10 ampere, but it was measured at a field current of 1.5 ampere. So OC and SC both are measured at two different field currents. Therefore, direct values will not give you correct answer for ZS. So I wanted to know open circuit voltage and short circuit current at same field current. Okay, and what I am going to do is that I will look at this short circuit characteristics. Why? Because we know short circuit characteristics are linear or non-linear. Linear, straight line passing through origin. See that? If I draw short circuit characteristics by taking field current on x-axis, short circuited armature current on y-axis, it is like a straight line passing through origin. What is a given field current? 1.5 ampere gives you a short circuit current of 10 ampere. See, when field current is, let us say IF1 equal to 1.5 ampere, yes or not? When field current is 1.5 ampere, armature current corresponding to this, the armature current value was 10 ampere, IA1 is, or ISC1 if you're confusing, ISC1, short circuit current. So ISC1 is equal to 10 ampere. Okay, but I wanted to know what is the short circuit current at a field current of 2.3 ampere. Okay, just a moment, guys. Okay, all right, just got a call. Okay, fine. So at a field current of 1.5 ampere, the short circuit current was 10 ampere, but I wanted to know what is the short circuit current at a field current of 2.3 ampere. If a field current is 2.3 ampere, what is the short circuit current? Okay, so let's see what is a short circuit current. I wanted to know what is the new short circuit current if the field current was 2.3 ampere. Why I am doing that? Why? Because open circuit voltage was already calculated at 2.3 ampere of field current. Therefore, I wanted to know what is the short circuit current at 2.3 ampere of field current. Okay. So see, as it is like a straight line passing through origin, what is the relation? Short circuit current is directly proportional to field current, right? Straight line equation. Therefore, ISC1 divided by ISC2 is equal to IF1 divided by IF2. What is a short circuit current in the first case? 10 ampere divided by short circuit current in the second case, that is the answer we need, is equal to field current in the first case 1.5 ampere by field current in the second case 2.3 ampere. Just cross multiply, you will get short circuit current in the second case. So let me complete the calculation. Yes, so 2.3 into 10 by 1.5. So I'm getting 15.33. This is the short circuit current at how much field current? 2.3 ampere. Now I know open circuit voltage and short circuit current at the same field current. So I can calculate what is ZS. So what is the formula for ZS? ZS is equal to open circuit voltage at 2.3 ampere of field current divided by short circuit current at the same 2.3 ampere of field current. What is open circuit voltage at 2.3 ampere of field current? 400. Remember, that is line to line voltage. But we have to use phase voltage only. As the machine is star connected, phase voltage will be equal to line voltage divided by root 3. Therefore, it is 400 divided by root 3. divided by what is the short circuit current at 2.3 ampere of field current? 15.33. Remember, it's a phase current directly given, all right or not? Okay, so to 15.33. 15.33. So if you take the ratio between these two, you will get a synchronous impedance. Let me calculate. 400 by root 3 divided by 15.33. Yes, I am getting 15.06 ohm per phase. That is the value of synchronous impedance. Okay, and that is a simple question given for 2 marks in GATE 2014 examination. Okay, right. The answer is 15.06 ohm per phase. Right. Now, let's try to answer one more question. This is a question from GATE 93 paper. This is also a question related to characteristics of synchronous generators. See the problem. A 3-phase alternator has negligible stator resistance. A short circuit test is conducted on this alternator. Short circuit test is conducted on alternator. At a particular speed, a field current of IF is required to drive the rated armature current. If the speed of alternator is reduced to half, what is the field current required to maintain same rated armature current? So simple. Question is about short circuit test. Initially, a field current of IF is required to circulate rated armature current. But now, speed of the machine is reduced to half. Alternator speed is reduced to half. Alternator speed is reduced to half. What is the new field current required to circulate same rated armature current? First of all, you remember in the short circuit test, what is the formula for armature current during short circuit? Is it not simply EF divided by ZS? Right? What is EF formula? 4.44 into field flux into frequency, number of turns into winding factor divided by ZS means can I write RA plus JXS, but RA is very small. I can approximately write it as XS only. And we know XS is an inductive reactance, so you can write it as 2 pi FL. Therefore, this is 4.44 into field flux frequency number of turns into winding factor by 2 pi F into L. So what happens here is that numerator and denominator frequency will cancel. Therefore, your observation is very simple. Short circuited armature current is independent of frequency. Whatever may be the frequency, short circuited armature current will be same. Okay, this is the point you have to understand. What is the modification happened in the question? Speed of the alternator is reduced to half. What is the factor that will change whenever speed reduces? Frequency will reduce. But a short circuit current is dependent on frequency or independent of frequency? Independent of frequency. Therefore, it doesn't matter what is the speed of the alternator, armature current remains the same in short circuit condition. Okay, on what factor it is dependent on? It is only dependent on field flux, independent of speed at which the machine was rotating. Okay, so I can write short circuit current, especially at a steady state. At a steady state is independent of rotor speed. Is independent of rotor speed. Okay, right. So therefore, what is the answer? Initially, if you need a field current IF, even in the later case also, you need the same field current IF. Okay, same field current. Got it? Yes. So that is the answer. Okay. Fine. So I added one more question related to the characteristics of a synchronous generator. This is a question from GATE 2017 paper. Therefore, good number of questions are there from characteristics of alternator. Read the problem. A 25 kVA 400 volt delta connected 3-phase cylindrical rotor synchronous generator. It requires a field current of 5 ampere. See, it requires a field current of 5 ampere to maintain rated armature current under short circuit conditions. So once again, short circuit data was given. How much field current is required? 5 ampere field current is required to maintain rated armature current. Next, continue. For the same field current, see, for the same field current, that means they are not changing the field current. The open circuit voltage was 360 volt. Okay, yes. Neglecting armature resistance, see, armature resistance is neglected. And magnetic saturation, its voltage regulation when generator delivers rated load at 0.8 power factor leading at rated terminal voltage is. This is a 2 marks question. So first of all, you need to understand short circuit test data was given, open circuit test data was also given. First of all, what is the power rating of this machine? 25 kVA, 400 volt, delta connected. First, let me note down the power details. The rated details. Yes. So the VA rating of the machine is 25 kVA. Okay. Terminal voltage of the machine, how much? 400 volt. This is line voltage. Machine is delta connected. Please remember. Machine is delta connected. Normally, most of the cases alternators are star connected, but here it is delta connected. So what I will do is, by using this kVA rating, I will try to calculate rated armature current. What is the formula for VA rating? We all know that VA rating formula, you can write two formulas. One is √3 VL/IL, line voltage, line current. Another one, 3 V phase, I phase. Any formula I can use. I am writing 3 V phase, I phase, so that I will directly get phase current. What is the VA rating? 25 kVA, that is 25 into 10 power 3 is equal to 3 into, what is the phase voltage? Yes, line voltage was 400. That means, can I say phase voltage is also 400 because machine is delta connected. And phase current is the unknown. You try to calculate this phase current. This phase current is indirectly equal to armature current at rated condition. Okay, so use the calculator. 25 into 10 power 3, 25,000 divided by 1200. So this was 20.83 ampere. This is the phase armature current value. Armature current per phase, 20.83 ampere. Now, let us note down the short circuit test details. In the short circuit test, it was clearly given a field current of 5 ampere to maintain rated armature current under short circuit. That means, what is the short circuited armature current? Rated armature current 20.83. Yet how much field current? Yet a field current of 5 ampere. Okay, right. Next, open circuit test details are also given. What are the details about OC test? It was clearly mentioned for the same field current. Field current is the same. The open circuit voltage is 360 volt. The open circuit voltage is 360 volt at same field current. That means field current is 5 ampere. Therefore, using this OC test and SC test data, can I calculate synchronous impedance? What is the formula? We know synchronous impedance is equal to open circuit voltage divided by short circuit current. Both must be measured at same field current, that is 5 ampere. Okay, so therefore, what is the OC voltage? 360. By default, that 360 is line voltage, but in this question, line voltage and phase voltage both are same because machine is delta connected. So 360 divided by, what is the short circuit current? 20.83. Remember, this is directly phase current, guys. Same phase current I am using here. Okay, so calculate what is the synchronous impedance. So 360 by 20.83, this is 17.28 ohm. That is the synchronous impedance of the alternator. But if you read the question carefully, armature resistance is neglected. See, neglecting armature resistance. That means RA neglected. When RA is neglected, can I say this ZS value is equal to XS simply? Okay. So I can go to the next page. RA neglected. Therefore, XS is equal to ZS. How much is coming? That is 17.28 ohm. Okay. Now, once you know what is RA and XS values, I think you can easily calculate what is the voltage regulation. Okay. Now calculate voltage regulation. To calculate voltage regulation, I need two values. What is the formula for percentage voltage regulation? EF minus VT by VT into 100. Okay, VT was already known, rated voltage 400 volt. Remember, we have to calculate voltage regulation at rated terminal voltage, that is 400. So unknown value was EF. Let us calculate EF using the formula. What is the formula we know about EF? Square root of VT cos phi plus IA RA whole square plus VT sin phi plus or minus IA XS whole square. All values must be per phase values. So let us substitute. What is VT under rated condition? 400. At what power factor we are asked to calculate voltage regulation? Yes, we are asked to calculate voltage regulation at 0.8 power factor leading. 0.8 leading power factor. So 0.8. RA was neglected. Therefore, I am directly writing VT sin phi 400 into what is sin phi? 0.6. If cos phi is 0.8, sin phi is equal to 0.6. Leading power factor, therefore this is a minus sign. And what is the value of armature current? Yes, rated current 20.83. 20.83 into what is the excess value? 17.28. 17.28 whole square. So if you solve it, you will directly get EF magnitude, voltage per phase, and then we can calculate regulation. So let us solve it. So 400 into 0.8, 320 square plus 400 into 0.6, 240. 240 minus 20.83 into 17.28 square. So I am getting 341.73. 341.73, that is the magnitude of induced EMF. So once you know induced EMF, I think I can go back, calculate what is the voltage regulation. Okay, so what is the formula for voltage regulation? EF 341.73 minus VT 400 by 400 into 100. This will directly tell you what is the voltage regulation. So 14 minus 14.56 percentage. Minus 14.56 percentage. That is the voltage regulation value. Okay. So the only doubt I have while solving this question is my calculation correct or not? There is always a doubt because you are using virtual calculator. Any mistake may lead to wrong answers. That's why when a lengthy calculation was there, in order to be very sure, calculate once again. Okay. If you have time in the examination hall, you try to calculate once again. I'm trying to do that. Yes, 341.73, correct. Okay, so this is the voltage regulation of the alternator. So what we did here, first open circuit details and short circuit details are given in the problem. So using both the details, I calculated synchronous impedance. And once the impedance was known, as RA is already neglected, from that you will get excess. And using these details, we found voltage regulation, okay, by calculating EF. Simple problem, it will come for 2 marks. But be very, very clear. All the details given in the question, they are all line values most of the times. Okay, by default, they are line values. But in the calculations, we must always use phase values. And in the given question, the machine is delta connected. That's why line voltage and phase voltage are equal. Okay, and phase current was line current divided by √3. Okay, so yes, these are the example questions related to characteristics of synchronous generator. Okay, right. Now our next topic is power flow equations of alternator. Okay. Okay, just a moment, guys. I have a problem with my spectacles. Okay, just a moment. Okay, all right. So let's continue. We are discussing about power flow equations of alternator. So an interesting topic and also an important topic. See, our aim is to calculate the active and reactive powers generated by alternator. Yes, active and reactive power generated by alternator, and I would like to calculate both input power as well as output power of the alternator. Okay, right. So let us first draw the equivalent circuit of a synchronous generator. Okay, and then we will try to develop the active and reactive power equations. Okay, so if I draw the equivalent circuit, so this is the induced EMF of the alternator, induced EMF at an angle delta, because we know induced EMF will lead the terminal voltage by an angle delta, and then armature resistance of the machine and synchronous reactance XS, and finally the load will be connected here. Generally this load is nothing but infinite bus bar. Okay, the current passing through the load is armature current, and the voltage across the load is terminal voltage at an angle 0. So this is the equivalent circuit of a synchronous generator. Now I would like to calculate two equations. One is input power equation, second one is output power equation. We will first try to develop the output power equation of the alternator. Okay, that means very simple. If you calculate the power on the terminals of the alternator, on the terminals, that will be definitely output power. Okay, so output voltage into output current, that will be output power of the generator. Whereas if you try to calculate the power on this induced EMF side, can I say this is where the mechanical input will be given. So if you use induced EMF and generated current, that will be input power of alternator. Output voltage and output current, that is output power of alternator. So what we will try to do is that we will try to calculate complex power value, and then from that we can develop the active power and reactive power equations. Okay, so equations are very simple to derive also. I will try to derive because it is very simple. If it is a lengthy derivation, we can memorize the equation, but it is a simple derivation, so that we can do that. Okay, see that first I would like to calculate complex power output. Okay, I clearly said output, that means on the terminals. So it is simply output voltage Vt into output current conjugate. You know that complex power is equal to Vi conjugate. Understand? And remember, I am trying to develop this equation using equivalent circuit, and we know in the equivalent circuit all parameters are expressed per phase. Okay, therefore every parameter I am writing here, they are per phase values. Okay, so if you continue, the complex power output will be equal to Vt, means it is at an angle 0. And now coming to armature current equation, you tell me current was flowing from EF to Vt or Vt to EF. Definitely it is flowing from EF to Vt. So what is the nodal analysis equation? You can write Ia is equal to EF at an angle delta minus Vt at an angle 0 divided by the impedance. Can I write this resistance and reactance together as impedance at an angle theta, Zs at an angle theta, and you write the same current here. So it is EF at an angle delta minus Vt at an angle 0 divided by Zs at an angle theta. Don't forget whole conjugate. I don't know. Okay. One second. Okay, whole conjugate. EF at an angle delta Vt at an angle 0 by Zs at an angle theta, whole conjugate. So I will go to the next page to extend the equation. So complex power output is Vt at an angle 0 into EF at an angle delta minus Vt at an angle 0 by Zs at an angle theta, whole conjugate. I have just rewritten. And can I say complex power is nothing but active power plus J into reactive power. So therefore, active power output, if I want, can I say that is the real part of this equation? Reactive power output will be imaginary part of this equation. So to avoid confusion, so let us continue with the same complex power. Okay, right. So therefore, the complex power is equal to, what is the first term? EF into Vt divided by Zs is there. And if theta goes to the numerator, it will become delta minus theta. But remember, there is a conjugate, so it will ultimately becomes theta minus delta. Minus a second term, Vt multiplied by Vt, it is Vt square divided by Zs. If theta goes to the numerator, it will become minus theta. Minus theta conjugate will be plus theta. This is the complex power equation. But I wanted to calculate active power and reactive power separately. Therefore, what is active power equation here? Therefore, active power equation will be real part of complex power. Got it? What is the real part? We know when you expand any complex term into rectangular format, real part is nothing but cos coefficient, imaginary part is nothing but sine coefficient. So therefore, the real part will become cos coefficient, that is EF into VT by ZS cos theta minus delta minus VT square by ZS cos theta. This is the active power output from an alternator. Okay, remember all quantities are expressed per phase, therefore obviously this is per phase power. If you wanted to calculate 3-phase power, you need to multiply this formula with 3. Okay, this is active power output. Similarly, what is the formula for reactive power output? Can I say reactive power output means Q output? Is it the imaginary part of this complex power? Am I correct? Imaginary part means sine coefficients. Then it will become EF into VT by ZS sine theta minus delta minus VT square by ZS sine theta. This is the reactive power output of an alternator. Reactive power output. So we found both active power output as well as reactive power output, and you look at that, the equations are looking lengthy. Here what theta is representing? Theta is representing the impedance angle. Delta is nothing but the load angle or power angle. Understand? Okay. So now I wanted to simplify this equation. See, if I wanted to simplify this equation, what the simplest thing I can do? Yes, we can take an approximation in the equivalent circuit. What is the approximation we can take? We know out of this resistance and reactance, resistance is very small, so you can neglect this resistance. Suppose if the resistance part is neglected, the impedance will have only reactance part. Got it? So let us take the approximation and simplify these equations. Yes. What happens if RA is neglected? Okay. So if armature resistance is neglected, what will happen? So can I say if armature resistance is neglected, the impedance magnitude will become only reactance, correct? Also the impedance angle, what is theta? Impedance angle tan inverse XS by RA. So the moment you neglect RA, it will become tan inverse XS by 0 because armature resistance is neglected. XS by 0 is infinite. Tan inverse infinite is 90 degrees. Therefore, impedance angle becomes 90 degrees. And if you replace these two in the previous two equations, active power and reactive power, you will finally get the simplified formulas. The active power output becomes EF into VT by XS into sine delta, and reactive power output formula will become VT by XS into EF cos delta minus VT. So this is the final formulas for active power and reactive power if armature resistance is neglected. In most of the numerical questions, especially if you are writing an exam where calculator is not involved, armature resistance will be usually neglected so that you can use these approximate formulas. But at exam like GATE level, okay, as you have calculator with you, generally armature resistance value will also be given, then these original formulas we have to use. But the only question is, sir, how can I memorize these lengthy formulas? You need not to memorize, you can derive it. Because you see, in 2 steps you will get the answer for active power as well as reactive power. You first calculate the complex power, VI conjugate, and expand that complex power into real parts and imaginary parts. The real parts will give you active power and imaginary parts will give you reactive power. Okay. And then in case if armature resistance is neglected, this is more simple. You know, active power will be EF VT by XS into sine delta. Reactive power will be VT by XS into EF cos delta minus VT. Now these are per phase values, guys. I must say what per phase. This is VAR per phase. If you want three-phase power equations, you multiply these equations with 3. 3 EF VT by XS sin delta, 3 VT by XS into EF cos delta minus VT. You just multiply with 3, you will get three-phase power values. Suppose what if the quantities are in per unit values? No need to multiply with 3, because in per unit calculation, phase value, single phase value or three phase value will be same, right? So no need to multiply with 3 if quantities are in per unit. In case if the quantities are in actual values, you have to multiply them with 3. Okay, yes. So this is about output power equations of the alternator. Output power equations. But sometimes in the numerical questions, we may also ask to find input power value also. Remember, you can calculate input power in two ways. One is calculate output power and add losses to that. Output power plus losses will give you input power. Or else you can directly calculate what is the input power of the alternator as well. As I told you, from the equivalent circuit, remember the terminals where the load was connected, this is the output terminals. Therefore, I can treat this is the input side. Okay, so this is the input side of the alternator where mechanical power will be given. We know what generator will do generally. Generator will convert mechanical power to electrical power. Therefore, the input power is mechanical, and remember, mechanical power will have only active component. It do not have any reactive component. Therefore, I would like to calculate active power input to the machine. Yes, that means I need this voltage and this current. Obviously, active power means real part of VI conjugate. If you calculate VI conjugate, that will give you complex power. If you know complex power, how do you calculate active power out of it? Active power is simply real part of the complex power. Okay, so let us calculate input active power also. Remember, this is the voltage and this is the current. Okay, so let us calculate active power input. Active power input means it is the real part of conjugate power EF at an angle delta into IA conjugate. Got it? This is into, this is conjugate. Okay, so real part of EF at an angle delta, fine. And what is IA? IA we already know it is flowing from EF to VT, right? So therefore, it is EF at an angle delta minus VT at an angle 0 by ZS at an angle theta whole conjugate. Got it? So now let us further go ahead. This is the real part of, what is the first term? EF at an angle delta. EF at an angle delta, is it not EF square at an angle? This is delta, guys. This becomes minus delta because of conjugate. Okay, so delta minus delta, and theta goes to the numerator, it will become minus theta. Minus theta conjugate will become plus theta divided by ZS minus second term EF into VT. EF into VT at an angle, yes, delta is there. Theta goes to the numerator, it will become minus theta. Minus theta conjugate will become plus theta divided by ZS. Okay, so overall value will be real part of, what is the first term? EF square by ZS at an angle, delta minus delta becomes 0. So theta will be remaining, minus EF into VT by ZS at an angle, delta plus theta. So I just need real part of this. This is a polar form. Now expand into, rectangular form, then cos terms will be the real part. So therefore, what if I take real part of this? So if I take only real part of this, this will become EF square by ZS cos theta minus EF into VT by ZS cos delta plus theta, right? So this is going to be the active power input of the alternator. Active power input of the alternator, watt per phase. If you want three phase value, you just multiply the equation with 3. So you can see this is active power input. Why I am not calculating reactive power input? Because input is a mechanical domain. On the mechanical domain, only active power will be available. Okay, whereas output is an electrical quantity, electrical domain. This is electrical domain. On the electrical domain side, we have active power quantity and reactive power quantity also. This is mechanical power domain, so only active power will be available since it is mechanical domain. Got it? Okay. So this is about input power of the alternator. But if I wanted to simplify, you can't obviously memorize these equations, learn the derivation part. It's a very simple derivation, simply VI conjugate. So now what I'm asking you is, can you simplify this equation? What is the thing you can do to simplify this equation? Neglect armature resistance. See what happens if we neglect armature resistance. If we neglect armature resistance, what will happen, guys? The ZS value will become XS and impedance angle will become 90 degrees. Theta becomes 90 degrees. Therefore, what will be the input power now? Yes, I will go back. Yes, look at the formula. This is EF square by ZS into cos theta minus EF into VT by ZS cos delta plus theta. Cos delta plus theta. Now just replace theta equal to 90 degrees. What is cos 90? Is it not 0? Therefore first product becomes 0. What is cos 90 plus delta? Cos 90 plus delta will be minus sin delta. Therefore overall it will become EF into VT by ZS becomes XS sin delta. So look at this. This is the formula for input power if armature resistance is neglected. Okay, watt per phase. Now, interesting thing is, this equation, input power when RA is neglected and output power when RA is neglected, can I say both are exactly same? Yes, output power when RA is neglected, EF VT by XS sin delta, and input power when RA is neglected, EF VT by XS into sin delta, both are same. Why? Because the moment I said armature resistance is neglected, indirectly losses are neglected. So the moment I said losses are neglected, output power and input power remains the same. Got it? So therefore, whenever armature resistance is neglected in alternator, input power value and output power value become equal. Understand? But when armature resistance was given, both equations are different. You see, what is the input power when armature resistance is considered? Yes, you see that EF into VT by ZS cos theta minus delta minus VT square by ZS into cos theta. But what is the input power? EF square by ZS into cos theta minus EF into VT by ZS into cos delta plus theta. Got it? So both equations are slightly different when armature resistance is considered, and both are exactly same when armature resistance is neglected. Okay? Got it? Okay, so these are the power flow equations. Now what we will try to do is that we will try to calculate the condition for maximum power values. Okay, yes, condition for maximum power, and we will develop two conditions. One is a condition for maximum active power and the second one is a condition for maximum reactive power. Okay, condition for maximum power output. Condition for maximum power output. Okay, so first we will try to understand when armature resistance is considered, what are the conditions? When armature resistance is neglected, what are the conditions? First of all, how to identify condition for maximum power? Very simple. To find out the condition for maximum active power, differentiate the active power equation with respect to load angle and equate it to 0, because we wanted to find out condition for maximum active power with respect to load angle. That means at what load angle active power will be maximum. That is what we wanted to identify. So therefore, differentiate this active power value with respect to load angle and equate it to 0. Okay, so then you will get a condition like delta is equal to theta. This is the condition. If delta is equal to theta, then active power will be maximum. Understand? Okay, delta is equal to theta. But if armature resistance is neglected, suppose if RA is neglected, what is going to be that theta value? 90 degrees, right? Therefore, delta will be equal to 90 degrees. Okay, so this is the condition for maximum active power. Similarly, we will find out what is the condition for maximum reactive power. Maximum reactive power. Then what you do? Very simple. Again, the same conclusion. Differentiate the reactive power with respect to load angle and equate it to 0. Then you will get the condition for maximum reactive power, and the condition will be delta is equal to 90 degrees minus theta. So this is the load angle at which maximum reactive power can be achieved. Suppose if load angle is, let us say, 80 degrees, maximum reactive power can be developed exactly at an angle delta 90 minus 80, that is 10 degrees, like that. So what if armature resistance is neglected? Suppose if RA is neglected, remember, neglecting armature resistance is a valid approximation because RA is very small. So if armature resistance is neglected, we know what is theta when RA is neglected, 90. So 90 minus 90, so 0 degrees. Therefore, maximum reactive power can be generated if load angle is 0. Maximum active power can be generated when load angle is 90 degrees. These are the conditions. When you know condition, how to get magnitude of those powers, replace these conditions in the respective equations. Okay, suppose if you look at active power equation, yes, this is the active power equation. What is the condition for maximum active power? Delta must be equal to theta. So if you replace delta is equal to theta here, theta minus theta becomes 0, cos 0 is 1. Therefore, what is the maximum active power? Therefore, maximum active power will be EF into Vt by Zs. Cos 0 is 1 minus Vt square by Zs. What is cos, theta is equal to, theta remains constant. So this is the maximum output power. Okay, maximum output active power. Similarly, what is maximum reactive power also you can find out. What is the delta must be 90 minus theta. Okay, 90 minus theta. Then you will get maximum reactive power as well. Okay. Similarly here, if RA resistance is neglected, then active power maximum will be delta is equal to 90 degrees, then sin 90 is 1. So active power maximum value will become EF into Vt by Xs. Reactive power maximum, delta is 0 degrees. What is cos 0 is equal to 1? Then it is Vt by Xs into EF minus Vt. That is reactive power maximum. Okay. When RA is considered, what is reactive power maximum? What is the condition? Delta is equal to, yes, 90 minus theta. You just replace 90 minus theta here, you will get what is going to be the reactive power value. Got it? Okay. So this is about the power flow equations of an alternator, both input power as well as output power. And we also discussed about condition for maximum powers as well. Now we will try to answer a question related to this concept. Okay. Yes. Active power and reactive power based one question we will try to answer. Okay. But before solving numerical question, I would like to discuss about power flow equations of motors also, so that together we can solve the problem, generator questions and motor questions. So let us consider the power flow equations of synchronous motor as well. And they are very similar to generator, but the only thing is, for motor, input will be electrical and output will be mechanical. Also, induced EMF will lag the terminal voltage by an angle delta. Okay, so let us write down, just a moment, power flow equations of a synchronous motor. Okay, yes. Power flow equations in synchronous motor. Okay, so let us try to understand power flow equations of synchronous motor. Okay, first let me draw the equivalent circuit. In a synchronous motor, the induced EMF is at an angle minus delta, so it will lag the terminal voltage by an angle delta. And armature resistance RA, synchronous reactance XS, and then we have terminal voltage here, terminal voltage at an angle 0. Got it? And armature current will flow like this. So therefore, let us calculate input power as well as output power. Remember, it is a motor, guys. Motor means terminal side, that is, this is the input. Okay, this is the input, where input is electrical, guys. When I say it is a electrical domain, you will have active power component as well as reactive power component. Active power input and reactive power input. Can I say this is going to be now mechanical domain? Mechanical domain, and this is output part of the machine. Output part, and there will be only active power. Why? Because when it is mechanical power do not have a reactive term. Mechanical power will have only active term, right? Okay, so we will calculate output active power. But on the electrical domain, input side, input active power as well as input reactive power we have to calculate. So first we will try to develop complex power input. Okay, so can I say complex power input will be simply Vt into Ia conjugate? Yes, that is input side. Whereas in generator, Vt into Ia conjugate is output. Okay, so if I proceed further, so complex power input is equal to Vt is at an angle 0. Okay, now look at that armature current. It was flowing from Vt to Ef or Ef to Vt, Vt to Ef. Therefore, what is the formula? Vt at an angle 0 minus Ef at an angle minus delta divided by Zs at an angle theta, and don't forget that we have to conjugate it. Okay, let's go to the next page and we will write the equation again. So therefore, input complex power is equal to Vt at an angle 0 into Ia, Vt at an angle 0 minus Ef at an angle minus delta by Zs at an angle theta whole conjugate. Okay, so let us multiply Vt into the bracket. Then what is the first term? Vt into Vt, Vt square. Theta goes to the numerator, becomes minus theta conjugate is plus theta. Therefore, this is Vt square by Zs at an angle plus theta minus Ef into Vt by Zs. If theta goes to the numerator, minus theta minus theta conjugate will be plus theta plus delta. Got it? Now, in this equation, what is going to be active power input, real part, reactive power input, imaginary part. So therefore, active power input will be the real part. Real part means cos terms, right? So Vt square by Zs cos theta, just a moment, cos theta minus Ef into Vt by Zs cos delta plus theta. This is active power input of this alternator. Remember, the answer is watt per phase. If you want a 3-phase input active power, you multiply the equation with 3. If you want per unit quantities, no need to multiply with 3. Next, what is the reactive power input formula? Imaginary terms. Imaginary terms means the first term becomes Vt square by Zs into sin theta minus Ef into Vt by Zs into sin delta plus theta. So this is reactive power input of a synchronous motor. Okay, so normally in regular class, we don't study generators and motors just like that. Okay, we will first study all the concepts of generators. Later we will study the concepts of motors. But side by side I am doing because it's a quick review session and like a revision. Okay, yes. Even in your revision also you have to do the same. Compare generator equations and motor equations. Generator phasor diagram, motor phasor diagram, everything. Okay, right. Now this is input active power and input reactive power. But what if I neglect armature resistance? Can I simplify the equations? Yes, we can. So what if I neglect armature resistance? Let's go to the next page. If Ra is neglected, what are the changes you can observe? Impedance will become Zs. Impedance angle theta becomes 90. Then what is a theta 90 means what is cos 90? 0. What is a cos 90 plus delta? Minus sin delta. Minus into minus becomes plus. Therefore, the input active power becomes Ef into Vt by Xs into sin delta. This is the active power per phase if Ra is neglected. Got it? Is it the same equation in generator also? Yes. Even in generator also, the output active power when armature resistance is neglected is same formula. Ef into Vt by Xs into sin delta, that is output power, but here it is input power. Similarly, what is going to be the reactive power input? if RA is neglected? Yes, it will be Vt by Xs into Vt minus EF cos delta. This is VAR per phase. Okay, so this is the reactive power input if armature resistance is neglected in a synchronous motor. What is the same formula in a synchronous generator? Output reactive power Vt by Xs into EF cos delta minus Vt, but here it is Vt by Xs into Vt minus EF cos delta. So the formula slightly changed. Okay, now these are about input power values. Now I would also like to calculate output power. Indirectly, this is the mechanical power developed by synchronous motor. Okay, because output is mechanical quantity. As I said, mechanical quantity will have only active power. So can I say active power is simply a real part of this voltage multiplied by this current? The voltage is EF at an angle minus delta. Current is IA. Okay, so VI conjugate, and the real part of that will be active power. Okay, so therefore let us see output active power. So I will directly write the equation. Output active power. This is the real part of EF at an angle minus delta into IA conjugate. Got it? Voltage was EF at an angle minus delta. Current is IA conjugate. Now I can extend the real part of EF at an angle minus delta, and what is armature current? It was flowing from Vt to EF, right? Vt at an angle 0, EF at an angle minus delta by Zs at an angle theta whole conjugate. Got it? So this is the real part of what is the first term? EF into Vt, EF into Vt by Zs. If theta goes to the numerator, it will become minus theta minus delta, but conjugate is there, therefore theta minus delta, correct? Okay, second term EF into EF square by Zs. You see this is minus theta, guys, but this minus delta, this minus delta conjugate will become plus delta, minus delta plus delta will cancel, minus theta conjugate will become theta, right? Now I just need real part of it, therefore can I say cos terms? Therefore the output active power, indirectly this is the mechanical power, guys, okay, is equal to EF into Vt by Zs cos theta minus delta minus EF square by Zs cos theta. So this is the output active power of synchronous motor. Okay, this is the output active power. Got it? And this is the input active power. Input active power of synchronous motor. So Vt square by Zs cos theta minus EF into Vt by Zs cos delta plus theta. This is output active power. EF into Vt by Zs cos theta minus delta minus EF square by Zs into cos theta. But what if I neglect armature resistance? Suppose if RA is neglected, what will happen? RA is neglected means indirectly losses are neglected. That armature resistance will have copper loss in it. If losses are neglected, you can check this output power equation becomes equal to input power equation. You can check that. Why? Because if RA is neglected, what is the theta is equal to 90. What is a cos 90 minus delta? This will become sin delta. Cos 90 becomes 0. Therefore, the answer will become EF into Vt by Zs becomes Xs sin delta. This is the same equation for input power also. Yes. So that means what? Whether it is generator or motor, if armature resistance is neglected, output power value and input power value becomes equal. That means we are indirectly neglecting the losses. But when armature resistance was given, you need to be very careful. Why? Because both are quite different. Understand? So this is about power flow equations of a synchronous motor. As I said already, these the actual power formulas, like when armature resistance was given, you cannot memorize them. You cannot. In generator as well as in motor. So the only way is understanding the derivation. Just in 2 steps, you can derive those equations. They are not difficult at all. Understand? Okay. Fine. Now, once we are done with the power flow, equations, now we will try to understand what are the different types of excitations we have in synchronous machines. Types of excitations. Then we will solve numerical questions. Types of excitation. Types of excitations. Okay. So actually, in order to understand the types of excitations, we have to draw the phasor diagram. From the phasor diagram, we have to understand how over-excitation, under-excitation and normal excitation can be observed. But as it is a quick session, I don't want to do the entire phasor diagram, derivation, etc. Directly we will write down what are the different types of excitations we have in a generator as well as in a motor. Okay. Now, see that. For one case, I will do with the derivation. Remaining cases I will directly write down, okay, without doing the derivation. Similarly, you can do it on your own, okay. After the class, you take a paper and pen and do on your own. One case I will do it, okay. What is that case? I will take a synchronous generator feeding a lagging power factor load. I will take a synchronous generator feeding a lagging power factor load, okay. That means you see, I have a generator with me. This is a generator. And this generator was feeding a lagging power factor load. Lagging power factor load means it is feeding an RL load simply. Yes. This is the load branch. Okay, RL load. Generally, what resistor will do in the load side? What is meant by RL load? RL load means this resistor will draw active power. It will consume active power. As resistor was demanding active power, our generator has to generate active power, obviously. Next, what inductor will do in the load side? We all know property of inductor in power system. Inductor will absorb reactive power. Inductor will consume reactive power. Therefore, as a load is consuming reactive power, our generator has to generate reactive power. That means what? When the load is a lagging power factor type, synchronous generator has to generate active power as well as reactive power. Okay. So active power is generated by the machine. Similarly, reactive power is also generated by the machine. Reactive power is also generated by the machine. Now we will develop the KVL equation and we will draw a phasor diagram. What is a KVL equation in generator? If you draw the equivalent circuit in a generator, this is EF, armature resistance RA, synchronous reactance XS, and here we have the load. And the voltage across the load is nothing but terminal voltage at an angle 0, and this is armature current flow. So what is the KVL equation? I will write in the next page or else here also. EF, phasor EF is equal to VT plus IARA drop plus IAXS drop. This is the KVL equation. Remember, everything is a phasor. You cannot add algebraically, we have to add them vectorially. Okay, so let us draw a phasor diagram satisfying this KVL equation. I will go to the next page. I will rewrite the KVL equation. EF is equal to VT plus IARA plus IAXS. Okay, so to draw the phasor diagram, I will take VT as reference first, terminal voltage. This was taken as reference. And what type of load I am considering? Lagging power factor load. Therefore, armature current will lag this terminal voltage. Armature current is lagging the terminal voltage by a power factor angle phi. Now, for this VT, which drop I have to add first? I have to add IARA drop, which is a resistance drop. We know resistance drop means, can I say it is in phase with current? Obviously, yes. So therefore, IARA is in phase with current. Now, what is the next drop? IAXS. We know IAXS is inductive reactance drop. Remember, this is XS, guys. This is an inductive reactance drop. Therefore, it will lead the current by 90 degrees. IAXS will lead this current by 90 degrees. This is IAXS. Now, what is the sum of VT plus IARA plus IAXS? Is it not induced EMF EF? And the angle between this EF and VT, this is what we call it as load angle delta. load angle delta. Okay, now what I am going to do is that I will make a small modification to this phasor diagram. Okay, see this, what I am doing is just to extend this VT phasor and draw a 90 degrees line here. I hope you are finding a right angular triangle. Understand? Okay. So in this right angular triangle, what is this length? Is it not VT? Let us call it as O. This point is A. Then what is this particular point is representing? Let us say this is representing B. This point is representing C. This point is representing D. Okay. Now tell me, this is phi, guys. Power factor angle phi. Then can I say this angle is also going to be phi only? Why? Because IA and IARA both are in phase. So if this is phi, automatically this is also phi. If this is phi, could you tell me what is this length AB? Yes, that AB length is nothing but equal to IARA cos phi. IARA cos phi. Got it? IARA cos phi. Next, what is this OA length? OA length is already VT. So OA length is already VT. Got it? Then what is this overall length OC? OC. What is OC length? I hope you are understanding the triangle, right? Look at this right angular triangle. In this right angular triangle, this is angle delta, guys. Okay. If this is delta, OC length is nothing but adjacent side of delta. Adjacent side of delta means, is it not EF cos delta value? Yes, this OC length is EF cos delta. Now my question here is that OA length is VT. This small length AB is equal to IARA cos phi. Now then what is this entire OB length is equal to? Is it not VT plus IARA cos phi? Okay. And what is this OC length? EF cos delta. So can I write length OC is greater than the length of OA plus AB together? Please try to understand the right angular triangle. This length OC, total length OC is greater than sum of this OA plus AB, because this BC is the extra length, right or not? So I can write OC length is greater than OA plus AB length. What is OC length here? EF cos delta is greater than, what is OA length? Can I say OA length is nothing but VT and AB length is nothing but IARA cos phi? Got it. Now take this IARA cos phi to the left side. Therefore, EF cos delta minus IARA cos phi is greater than terminal voltage. This is interesting. Okay, so if this condition is satisfied, that particular synchronous generator is known as over-excited synchronous generator. This is what we call it as over-excited. This is known as over-excitation. Remember, over-excitation means, you look at this EF cos delta, this is indirectly induced EMF component. This is the terminal voltage component. So the induced EMF component and the terminal voltage component both are in phase, guys, right now. You see that this EF cos delta means this OC length. VT means this OA length. Can I say VT and EF cos delta both are in phase with each other? So I am comparing two voltages which are in phase with each other. Got it? So therefore, whenever EMF component and VT component which are in phase with each other, when I compare both of them, induced EMF component is definitely more than terminal voltage. When I say induced EMF component is more, field excitation is more, because EMF component will depend upon excitation voltage, right? So when I say excitation was more, that is what we call it as over-excitation condition. Over-excitation. So over-excitation means EF cos delta minus IARA cos phi must be greater than terminal voltage. But what if RA is neglected? Most of the times we will study this condition by neglecting RA. Okay, suppose if RA is neglected, tell me what is going to be this IARA cos phi. Can I say this becomes 0? Therefore, the condition is simply EF cos delta is greater than terminal voltage. EF cos delta is greater than terminal voltage. So whenever this condition is satisfied, then you can conclude the system is over-excited. Over-excited. So over-excitation means EF cos delta is greater than terminal voltage. Never compare EF and VT for excitation. You have to compare EF cos delta and VT. EF cos delta and VT. Then only we will get correct understanding of excitation. But the rule is, the strict equation is this one. EF cos delta minus IA RA cos phi is greater than VT. That is over excitation. But normally RA is neglected. Then this is the condition. Okay. Also, in this particular case, what if you calculate reactive power equation? You remember what is the reactive power output of an alternator? VT by XS into EF cos delta minus VT. Remember, this is the equation when RA is neglected. And right now I said EF cos delta greater than VT. If EF cos delta is greater than VT, this difference will become positive. Therefore, reactive power will become positive. So therefore, when the system is overexcited, reactive power is positive. And this overexcitation phenomena we are observing when machine is at which power factor? Lagging power factor. Don't forget the machine is a generator. Now what if I apply the same concept to leading power factor? Then leading power factor means you will get RC load here. R will obviously absorb active power, therefore generator will generate. But what C will do in the load side? We know the property of capacitor. Capacitor will generate reactive power. If load capacitor was generating reactive power, our alternator will absorb reactive power. Therefore, the reactive power will be absorbed. It will become under excitation and reactive power becomes negative. Okay, so I don't want to do that derivation once again. You can do it on your own for leading power factor now. Okay, so I will directly write down a tabular column so that you can get everything. Okay, so what I am trying to do is generator first I will take. Generator. Okay, 3 power factors we will discuss. Lagging power factor case, leading power factor case, unity power factor case. Okay, generator lagging power factor means what is the excitation? Over excitation. We just studied. Over excitation. That means EF cos delta is greater than VT. Okay, EF cos delta greater than VT. And what is the reactive power status? Reactive power is generated and reactive power is positive. This is when the generator was feeding which type of load? Lagging power factor load. What if it is leading power factor? We will get under excitation. Under excitation. Under excitation means EF cos delta becomes less than VT. And reactive power is absorbed by the machine rather than generating. Machine will absorb reactive power. Also, the sign, the reactive power becomes negative. You can check this by using equations. You can check this. Okay. Next, what about unity power factor? Unity power factor is what we call it as normal excitation. Normal excitation. Normal excitation means EF cos delta will be exactly equal to VT. It is neither more nor less, it is exactly equal. And in this case, reactive power will be 0, neither generating nor absorbing. Okay, it is neither generating nor absorbing. And remember, this is all if RA is neglected. Remember, suppose if RA is considered, you will get this extra drop. Then you have to compare EF cos delta and VT, or EF cos delta minus IA RA cos phi minus IA RA cos phi. That should be greater than VT for over excitation, less than VT for under excitation, equal to VT if it is normal excitation. But most of the cases, RA will be neglected. So we are just comparing EF cos delta and VT. This is when the machine is a generator, guys. Don't forget. Okay. And what about active power flow? In all these cases, what is the status of active power? That doubt may also come. Reactive power sometimes generated, sometimes absorbed, sometimes neither generating nor absorbing. But what is the status of active power? Remember, if it is a generator, any power factor, active power is always generated. Okay, active power is always generated, because the property of a generator is to convert mechanical power to electrical power. Therefore, the electrical power is always generated, irrespective of the power factor. But active power is always generated. But reactive power flow will change from power factor to power factor. In a lagging power factor case, reactive power is generated, leading power factor case absorbed, unity power factor case reactive power is 0. Now in a similar fashion, we can do it for motor also. Okay, I don't want to do the derivation. I will directly write down this information. You try to analyze using phasor diagram, okay, of the motor. Yes. So let us understand motor also. Remember, RA is neglected. If RA is neglected, right? So once again, 3 power factors we are going to study: lagging power factor, leading power factor, unity power factor. Okay, but all powers I am talking about right now, they are input powers. For motor, the powers are input. For generator, the powers are output. So lagging power factor we will get under excitation, exactly opposite to generator. In generator, lagging power factor is over excitation. In motor, lagging power factor is under excitation. Under excitation means EF cos delta is less than VT. Okay, less than VT. Also, the reactive power will be absorbed by motor, absorbed, and the sign will be negative. Sorry, absorbed, positive sign will come. Reactive power will be positive and the machine is absorbing the reactive power. Now if you look at leading power factor, leading power factor means over excitation, exactly opposite to generator. In generator, leading power factor is under excitation, but in motor, leading power factor is over excitation. Over excitation means EF cos delta is greater than VT and reactive power is generated by the machine and it is negative. You can use formula, reactive power formula. If EF cos delta is greater than VT, definitely reactive power is negative. Now next one is unity power factor. Unity power factor means normal excitation. Normal excitation, that means EF cos delta is exactly equal to VT. It is neither over excitation nor under excitation, it's a normal excitation. And here reactive power is 0, neither generating nor absorbing. So what about active power status in all these cases? Whatever may be the reactive power, in whatever may be the power factor, active power is always absorbed by the machine only. Because what is the purpose of motor? Motor means it will convert electrical power to mechanical power. That means motor will draw electrical power, that is nothing but active power it will draw, and it will deliver mechanical power to the load. Understand? Got it? So once again, look at generator cases, lagging power factor and leading power factor and unity power factor. Take a screenshot, keep this image with you. It will be easy for you to revise. And this is motor for all the different power factors: lagging power factor, leading power factor and unity power factor. Everything you can prove by drawing the phasor diagram, but we are not doing that. In regular classes we used to do that, but in the revision you just try to revise this, that will be sufficient. Okay, so this is a generator excitation conditions, this is motor excitation conditions. Okay, yes, always understand how do you decide whether a given machine is operating at a lagging power factor or leading power factor. How do you decide? The power factor of a given machine you can decide based on the information of active power or based on the information of reactive power. Yes, active power information cannot tell you power factor. Why? Because you take a generator, any power factor, active power is generated by the machine only. Okay, you take a motor, any power factor, active power is absorbed by the machine only. Therefore, active power information will tell you whether the machine is a generator or motor. That's all. If it is generator, active power generated. If it is motor, active power absorbed. It will only tell you whether machine is a generating machine or motoring machine. But reactive power flow will tell you what is the power factor of the machine. If reactive power is positive in motor, it is lagging power factor. If reactive power is negative in motor, it is leading power factor. If reactive power is 0, unity power factor. In generator, if reactive power is positive, lagging power factor. Reactive power is negative, leading power factor. Reactive power 0, unity power factor. So therefore, power factor, whether it is lagging or leading or unity of any synchronous machine, you can understand by calculating reactive power value, not by calculating active power value. Got it? Yes. Now we will try to answer a question related to the power flow diagrams and the excitation conditions of the synchronous machine. Okay. All right. Let's see the questions now. Look at the first question. A three-phase 50 Hz star-connected cylindrical rotor synchronous machine is running as a motor. Yes, the question is from a motor. The machine is operated from 6.6 kV grid and draws a current at unity power factor. Synchronous reactance was given. Okay, see that synchronous reactance was given, but there was no information about resistance. That means you can neglect the resistance value. The load angle is 30 degrees. What is the power delivered to the motor in kilowatt? Okay, power delivered to the motor means the input power we wanted to calculate. Okay. So if you see, the machine is operated from 6.6 kV grid. This is obviously the line voltage. And draws current at unity power factor. One more information is current is at unity power factor. Okay. Load angle is 30 degrees. See, the next information available is load angle 30 degrees. So first let me note down the details. Terminal voltage, and it is a three-phase machine, guys. There is no information whether it is, yes, I think information is given. It is a star-connected machine. So line voltage 6.6 kV means what will be the phase voltage? Yes, I can write terminal voltage is equal to 6600 by root 3 volt per phase. Okay. Next information. Machine is operating at unity power factor. That means cos phi is equal to 1. That means sin phi is equal to 0. Next information, load angle is 30 degrees. Load angle is equal to 30 degrees. What is the active power drawn by this motor is the question. We wanted to answer the question in kilowatts. Current value was given or not given? No, there is no information about current drawn by the motor. Okay. They said current was drawn, but magnitude was not given. Okay. Yes. So what I can do here, first thing, RA is neglected in the problem, right? Yes, RA is neglected because there is no information about RA. RA was not given, that means RA is neglected. RA was neglected, that too, machine is at which power factor? Unity power factor. Unity power factor means, can I say normal excitation? Yes. Normal excitation. What is the condition for normal excitation? EF cos delta is equal to Vt. This is the condition for normal excitation. Okay. In this, we don't know what is EF, but we know the delta value, right? What is the delta given? 30 degrees. And the terminal voltage was 6600 by root 3. So if you solve this, we will get EF value voltage per phase. Okay. Let me get my calculator so that we will answer it. Yes. Okay, so what is EF value? 6600 by root 3 divided by cos 30. Yes, I am getting 4400 volt per phase. This is the EF magnitude. The moment I know the EF magnitude, I can calculate active power drawn by the motor. What is the formula for active power? Active power when armature resistance is neglected is 3 into EF into Vt by XS into sin delta. Remember, if you don't multiply that 3, you don't get 3-phase power. Okay. So now every quantity was known here. 3 into what is EF? 4400. What is Vt? 6600 by root 3 divided by what is the synchronous reactance that was given in the problem? 30 ohm. 30 ohm per phase is the synchronous reactance. Just substitute 30 ohm into sine delta value was equal to 30 degrees. Okay. So if I substitute all the quantities, I will directly get the answer for active power. You will get in watts, then convert to kilowatts. Okay. Let me do it. You can also do and let me know in the options. Okay, into 30 sine 30 degrees. Okay, I'm getting 838 kilowatt. Clarity I wanted to weigh 3 by 30 into sine 30. Yes, 838 kilowatt. 838.31 kilowatt. So actually you will get in watts, then convert to kilowatts. So this is the active power drawn by the motor. Suppose if the same question was given including RA. Suppose if RA is included. Okay, I may ask any question, right? Okay. So if RA is included, what will you do? If RA is included, then what is the observation? Yes, RA is included, that too unity power factor. Unity power factor means normal excitation. Now what is the condition for normal excitation when RA is included? This is motor, right? Therefore the condition is EF cos delta plus IA RA cos phi. This should be equal to VT. This is the condition for unity power factor. If you wanted to check it, draw a phasor diagram. You take VT as reference. Unity power factor means IA is in phase with VT. Now draw the drops, right? What is the IA excess drop and RA drop you have to draw. So if I draw IA excess will always lead the current by 90. Draw it on the bottom side of VT. Always remember it is a motor. In motor, the drop has to be added to EF, not to VT. This is IA excess. Okay, and this is IA RA. And this gap is nothing but EF. And this is delta. Okay, you can further extend this diagram. You just draw a line here. So this is 90 degrees, guys. Let us say this is O, this is A. What is OA length? VT. What is this OB length? Is it not EF cos delta? Yes, this is EF, this is delta. So OB length is EF cos delta. So OB length is EF cos delta. And this is IARA, guys. If this is IARA, can I say this BA length is also IARA? BA length is also IARA. And then what is the overall OA length is equal to VT. Therefore, what is the final conclusion? This OA length is equal to OB length plus BA length. What is OB? EF cos delta. Okay. What is this BA length? IARA. Can I write cos phi into cos phi because it is unity power factor? That's why cos phi is 1. This is equal to VT. Okay. That is what I have written here. If it is a generator, we already derived, if you remember. In a generator, one equation I derived. There you get minus IARA cos phi if it is generator. But in motor, current will reverse. Therefore, that is plus IARA cos phi. So if it is equal to VT, that is normal excitation. If it is greater than VT, over excitation. Less than VT, under excitation. But normally, majority of questions, RA will be neglected. So you will compare EF cos delta and VT only. Got it? Okay. Fine. Let us answer one more question. This is a question in GATE 2004 exam. A 400 volt 50 kVA 0.8 power factor leading 0.8 power factor leading delta connected case. Yes, it's a special case. Most of the cases connection will be star, but here it is delta, clearly mentioned. Delta connected 50 Hz synchronous machine has a synchronous reactance of 2 ohm, negligible armature resistance. Negligible armature resistance. The friction and windage losses are 2 kilowatt. Core losses are 0.8 kilowatt. The shaft is supplying 9 kilowatt at a power factor of 0.8 leading. What is the line current drawn? Line current drawn. They said line current drawn means the machine is definitely a motoring machine. Okay. Only in a motoring machine will draw the current. If it is a generating machine will deliver the current, right? So they are asking the line current drawn, therefore this is a motoring machine. Also, you can understand one more word they have said, shaft is supplying, okay, 9 kilowatt at a power factor of 0.8 leading. Okay, so that means the shaft supplying 9 kilowatt to a load, obviously mechanical load, right? So this is a motoring machine. So first let us note down the given information. 400 volt, that is line voltage by default. If line voltage was 400, can I say phase voltage was also 400 because machine is delta connected? Okay, yes, voltage was given. Next information is synchronous reactance was given, 2 ohm. There is no information about armature resistance and it was clearly mentioned armature resistance neglected. Losses are given. What are the losses given? Friction and windage losses are given. We call it as simply mechanical loss. Mechanical loss was 2 kilowatt. Is it? 2 kilowatt. Next, core loss is given, 0.8 kilowatt. Core loss is 0.8 kilowatt. Okay. Next information. Shaft power was given. What is a shaft power? 9 kilowatt. That is output power indirectly. So the output power was 9 kilowatt. Power factor was given. What is a power factor? 0.8 leading. Power factor cos phi is equal to 0.8 leading. One important observation is, as armature current is neglected, indirectly copper loss is 0. Got it? So the only resistance offering a copper loss is armature winding resistance. As armature resistance is neglected, copper loss is 0. Now you see, you know output power information, you know the losses information. So can you find out input power just by adding? Input power of any machine is always equal to output power plus losses. What is the output power in this question? 9 kilowatt plus losses means mechanical loss I have to add, core loss I have to add, copper loss I have to add, but fortunately in this question copper loss is 0. Therefore, what is the overall answer? It was 11.8 kilowatt. This is the input power. Okay. Now, how can I write formula for input power of any three-phase system? Yes, root 3 VL IL cos phi. Active power, right? This is 11,800 watt. Okay. If it is reactive power, root 3 VL IL sin phi. So, root 3 into what is the line voltage given in the problem? 400. Line current is the answer you have to find. Power factor was 0.8. Got it? This is 11,800. And if you solve it, you will get the current information. Directly line current you will get. In the question, what is they are answering? The line current drawn by the motor. If you want phase current, then it will be divided by root 3 because delta. So let us find out 11,800 divided by root 3 divided by 400 and 0.8. So I am getting 21.28 ampere. 21.28 ampere. This is the amount of current drawn by the motor. Okay. So 21.28 ampere. I think option C will be satisfied. 21.28 ampere. Okay. Yes, very simple question. Suppose if armature resistance is given, then you have to add copper loss also. How can you write formula for copper loss? Yes, you have to write it as 3Ia square Ra. Why I am multiplying with 3? Because to get 3-phase copper loss, right? And then this is Ia is per phase current, Ra is armature resistance. That will become copper loss in armature winding. But here the copper loss was neglected. Okay, it was a 2 marks question, very easy question. Okay, right. Now, let's see one more question. This is a question from GATE 2017 question paper. Read the problem. 1 mark question, easy. If a synchronous motor is running at a leading power factor, synchronous motor running at a leading power factor, its excitation EMF EF will be. Okay. See, synchronous motor leading power factor. What is the excitation, guys? Is it not over excitation? I told you. A motor at leading power factor, it is over excitation. Over excitation means what? EF cos delta is greater than VT. Let's go back to the question. Yes, here over excitation, right? I can write down over excitation. Over excitation means EF cos delta is greater than VT. Okay, now they are asking us to compare magnitude of EF with VT. Okay, so here I can write from this, I can write EF is greater than VT by cos delta. EF is greater than VT by cos delta. We know for any value of delta except 0 degrees, cos delta is always less than 1. EF is greater than VT by less than or equal to 1. Okay, if it is 0 degrees, cos 0 is 1. If it is some finite delta angle, it is less than 1. So 1 by less than 1, is it not greater than 1 again? So EF greater than VT. So what is the final observation? EF is definitely greater than VT. Got it? So therefore, when a synchronous motor is overexcited, induced EMF is definitely higher than terminal voltage. So option B will satisfy, higher than terminal voltage. Got it? Yes. This is a 1 mark and easy question. Next, we have a 2 marks question in GATE 2020, and it is also easy question but given for 2 marks. A 3-phase cylindrical rotor synchronous generator. The question is from synchronous generator this time, and it has a synchronous reactance XS. Negligible armature resistance, RA is neglected, so formulas becomes easy. The magnitude of per phase terminal voltage VA, okay, terminal voltage was written as VA, and the magnitude of per phase induced EMF was written as EA. Consider the following statements about P and Q. P is active power, Q is reactive power. Okay, I think, sorry, I'm wrong. P and Q are the statements. Okay, sorry. P and Q are not active power and reactive power, they are statements. Okay, fine. So P and Q, 2 statements are given. So which of the following statements are correct is the question. First, let us see statement P. For 3-phase balanced leading power factor, okay, leading power factor load across the terminals of synchronous generator, VA is always greater than, more than EA. See, first question is about leading power factor. What is mean by leading power factor? Under excitation, right? Because it is a generator. Generator leading power factor means under excitation. What does mean by under excitation? Under excitation means EF cos delta is less than VT. Got it? So from this, yes, we are asked to compare VA and EA, right? So yes, from this EF is less than VT by cos delta. Just now I told you delta, suppose if delta is 0 degrees, cos delta will be 1. But if delta is a finite angle, cos delta will be less than 1. So it should be either less than or equal to 1. So EF is less than VT by less than or equal to 1. What is 1 by less than or equal to 1? Is it not greater than or equal to 1? So EF is less than, greater than or equal to 1. So therefore you see you are getting 2 symbols here. Less than symbol is there, greater than symbol is there. Therefore you can't say this is not 1, greater than, equal to VT, right? This is VT. Okay, this is VT. Got it. So now suppose if this greater than value was dominating, EF is greater than VT. Suppose if this less than value was dominating, EF is less than VT. Suppose if both are cancelling each other, then you may get EF equal to VT also. That means you can't guarantee who is more, who is less unless you know the value of delta. Unless you are clear about delta, you can't estimate whether EF is less than VT or EF is greater than VT. Okay, now see the statement P. For any 3-phase leading power factor connected to the terminals of synchronous generator, VA always more than EA. This is wrong. It is not always more than. It may be more or it may be less. It depends upon what delta value. It depends upon delta. Without knowing the value of delta, you can't conclude whether VT is more than EF or less than EF. Got it? Suppose if delta is 0, what is cos 0? 1. If cos 0, 1, yes, VT is definitely greater than EF. But delta may not be 0 always, right? It may be 20 degrees, it may be 30 degrees, it may be 40 degrees. So unless you know the value of delta, you can't guarantee who is more, who is less. Therefore, statement P is wrong. Look at statement Q. Now, statement Q is about lagging power factor load. Now, tell me, a generator at lagging power factor means what is the excitation? Over excitation, right? Over excitation. A generator at lagging power factor load means over excitation. What is mean by over excitation? EF cos delta is greater than VT. You take delta to the right side. Therefore, EF is greater than VT by cos delta. Now we know cos of any finite angle is less than 1. Cos 0 degrees is equal to 1. Therefore, EF is greater than VT by less than or equal to 1. What about 1 by less than or equal to 1? Is it not greater than or equal to 1? Therefore, EF is greater than or equal to VT. Okay, see, already greater than symbol is there. Now another greater than symbol is there. Therefore, EF is definitely greater than VT. Or you can write VT is definitely less than EF. So it doesn't matter what is the delta value. Any delta value you take, VT is always less than EF. So now see, lagging power factor load connected to the terminals of the synchronous generator, VT always less than EA. Yes, this is correct statement. Always. It is always less than. VT always less than EF. Any value of delta. This is lagging power factor over excitation case. Therefore, the answer is P is a wrong statement. Q is a correct statement. So, option A was correct. P is a false. Q is a true. Got it? Yes. All right. So that's it. So these are the example questions that we got in the previous GATE exam. There are other questions also. You can go through previous GATE questions once and you can try to solve them. Okay. So now I would like to conclude the session here today. In the part 3, we will discuss about parallel operation, okay, V and inverted V curves of both generator and motor, etc. Okay. With this, I would like to conclude part 2 session. Now it's time for questions. Okay. So let me go through your charts. Any question, please let me know. I will try to give you the answer. Okay. Okay, so I'm going through the chat box. So any questions, please let me know so that I'll give you the reply. Yes, Sai Vikas, very good that you answered many questions. Wonderful. Vijay Vardhan, thank you for your answers. Okay, so I'm going through few of the questions. Please take a review on Sabhavat Priya. Yes, I will take in the third part. In the third part, I will cover salient pole rotor alternator, power flow equations, parallel operation, okay, V and inverted V curves of generator and motor, and also synchronous condenser. Okay. Right. Yes, zero voltage regulation is possible only for leading power factor. Right. That is correct. Maximum voltage regulation is possible only for lagging. Correct. Okay. Yes. Condition for maximum reluctance power. Reluctance power will be maximum when delta is 45 degrees. That we will see in salient pole machine. We have not yet come to that part. We call it as two reaction theory. That I will cover in the third part of this, synchronous machines. Okay, so Kalidas, actually a rotor part of synchronous machine is not laminated here. It is excited with DC, and also in order to create damping torque, okay, the circulating currents in the rotor will also create damping torque. Generally, we don't laminate rotor core. Unless it is a special machine, we don't laminate rotor core generally. Okay. Rotor core is generally not laminated. As I said, unless it is used for some special applications. Okay. Thank you, Srinivas. Thank you for your feedback. Yes, I'll do a separate session, Jayant. Expected interview questions from synchronous machines. So thanks for your idea. I will do one session for all electrical machines together. So when you go for MTech interviews or any technical interviews, what are the questions you can expect from electrical machines? I will do one session. Even if you go for ESC interview also, that will be helpful for you, right? Yes. Any more questions? Any more questions? So there are still some topics left in synchronous machines. Okay, it's already 2.5 hours. The session already 2.5 hours. So I will take a third session. In the third session, we will finish the subject. Keep practicing previous gate questions. Okay. Don't try to solve too many textbooks or too many material books or too many test series. So keep your resources very simple because you have to prepare so many other subjects also. Previous gate questions you have to thoroughly practice and take one online test series. That is sufficient. Okay. Drooping characteristics problem generally you will study in power systems. Okay. Load frequency control techniques. No problem. In the third session, I will try to take one problem. Okay. That is load sharing between alternators. Generally, in parallel operation, we will study this topic. Yes, I will take a problem. Don't worry. Okay. Any more questions? Okay, guys. So then we will conclude the session here today. All right. Right. Thank you so much. Please share this session with your friends. Also subscribe to our YouTube channel for regular updates and also these kind of lectures etc. All right. Meet you next time. Okay. Bye bye.